Hi everyone, I'm Álvaro Gaona. I'm part of the Laboratory of Artificial Intelligence and Robotics at the University of San Andres. And today I'm going to talk about one of our latest work for autonomous aerial vehicles, in particular, fault-tolerant solutions for multi-rotor UAVs using NVIDIA Jetson TX2 as our onboard computer of choice. In our agenda today, we got the following topics. Firstly, we will discuss about fault-tolerant vehicles and the design we propose. Fault detection and identification is another crucial topic to discuss, along with the fault-tolerant control scheme that makes these vehicles perfectly stable even in the event of a failure. Lastly, I'm going to mention a little bit about the autonomous landing platform and the integration with the fault-tolerant control and FDI modules. So now I would like to speak about our selected fault-tolerant design. Generally speaking, UAVs are not fault-tolerant in nature. We've seen that if one motor fails, then the UAV is bound to crash. In addition, we can say that the quad rotor cannot maintain full altitude and altitude if a rotor fails, as it's been proven that at least a minimum of 6 rotors must be available to accomplish controllability. Our vehicle design takes into account reconfigurable rotors to keep up with the control allocation law, capable of following reference trajectories and attain full altitude and altitude. Our platform consists of a commercial hexarotor frame, in this case a DJI F550 with 6 DJI brushless DC motors with 1 kg each, and the whole hexarotor weighs around 2.8 kg. The vehicle has 2 onboard computers. One is responsible for the low-level control, which has 2 closed loops for attitude and position running at 200 Hz. Then we've got an NVIDIA Jetson TX2 for vision-based autonomous navigation, an FDI algorithm. One of the modules of the fault-tolerant control software is the FDI module, responsible for fast and accurate detection and identification of the failure, for which a bank of observers could be implemented. On the other hand, we can learn from flight data and apply ML algorithms such as random forest or SPM. The former is able to run on low resource computers, and the latter one is more compute intensive. That's one of the reasons we've chosen to use the Jetson TX2. In the graph, we can see a flight in which at around 5.5 seconds, an engine failure was injected and the detection happened in about 185 milliseconds. This time can also be reduced, increasing the number of samples and the sampling frequency. Then we've got the fault-tolerant control. The vehicle switches between 2 predetermined states, from nominal to one of the possible failure states. As the geometry changes, so does the control allocation law, which relates the forces exerted by each motor to the vehicle thrust and torques exerted by the vehicle. This can be summarized as the equation in the left, where Q are the torques, Fc the vertical force, and F in boldface is a set of forces exerted by the 6 motors, and A is the so-called torque force matrix that relates these quantities, depending only on the mechanical characteristics of the vehicle. For example, the force torque matrix A for the vehicle in nominal state, that means no failure, is shown on the right side of the equation. Then, when a failure occurs, only the matrix A needs to be changed to consider the lack of the failing motor and the new orientation of one of the reconfigured ones. As all these possibilities are pre-computed, the vehicle only switches between a number of predetermined matrices. This allows to maintain the same control law, such as PID controller, and it keeps the control design simple. Now I want to show a video where a failure is injected and the fault-tolerant control software prevents the vehicle from crashing. As you can see, the vehicle takes off, and at around 6 seconds, the failure is injected and the software is capable of detecting the failure and reconfiguring the rotor to maintain its altitude and altitude. Now we can see again the same video but in slow motion. It's very clear that the forces are compensating for the failed motor, and then the controllability is attained again. Another solution is autonomous landing and the event of rotor failures. On the right, we can see an Intel RealSense camera mounted facing downwards to detect the landing pad using vision-based algorithms. In this case, we're using a landing pad constructed with 2 Aruco tags. The smaller one is useful when the vehicle lost sight of the bigger tag due to the proximity to the ground. These tags are quite useful even under occlusion of some bits One of the properties of these tags is that it's possible to detect the markers with partial information. That's the reason that using a tag on top of another tag is possible. We've also measured the maximum detection distance with a 640 millimeters by 640 millimeters tag, which is 28 meters. Thus, we can perform landing maneuvers up to that distance. The autonomous landing algorithm can also be integrated with the fault-tolerant control scheme, making it possible to land the vehicle in the event of a motor failure, as we've seen before. For future work, our group is interested in also detecting and identifying failures of onboard sensors, which has even more robustness to UAVs. Another interesting topic is trajectory planning for relocation of the landing pad in the event of disturbances. Strong airflows or even failure can cause the vehicle to drift from the nominal trajectory and lose sight of the landing pad. Therefore, it's crucial to perform a maneuver capable of relocating the landing pad and keep with the landing maneuver. And lastly, landing over previously unknown areas upon failure during a mission is important. At this point, we're interested in identifying a landing zone and successfully landing the faulty vehicle.